Hey everybody. So what we're going to do, and I'm looking to make sure all my lights are lit up on the camera, and it looks like they are. So what I'm going to finally do is cover a video I've been asked by many people for a couple of years, probably 5 years to do. I'm going to try to keep this video as short as I can, okay? I hate when videos go over 30 minutes, but there's a lot to talk about here. But what we're talking about is how to design large airplanes over 55 pounds, how to understand the systems that go in them, and just understand how it works. So I'm going to get to this first document that I created here. And it starts with the aircraft design considerations. So what are you going to consider when you build the entire airplane? Are you building a warbird? Are you building a transport plane? Are you building something that doesn't look like anything else? You're just experimenting to build a contraption plane. But here's some things that you need to figure out, okay? And a lot of times it starts out actually with just a piece of paper and a pencil or a pen, and you start sketching. And I normally will have a ruler and kind of figure out a scale. So you got to figure out what your wingspan is going to be. Sometimes the wingspan, if it's a scale airplane, you need to design that wingspan to fit in your car or your trailer. You need to understand what that wingspan means. You also got to think about how much money you want to spend on the airplane with the size and scope of the aircraft. So once you figure out the wingspan, if you're designing your own design, you got to figure out the wing chord. If it's scale, that wing chord will be corresponding to the wingspan. Select an airfoil. 90% of the time, a semi-symmetrical wing is probably the best airfoil to pick. The reason is that when you go fast with a semi-symmetrical wing, it just takes a little bit of down trim to fly level. A flat bottom wing will want to produce all kinds of lift, so you need a lot more down trim. And a fully symmetrical wing sometimes doesn't need to have much trim change. But semi-symmetrical wing is the most forgiving when it comes to slow speed. I'm sorry, that's not true. For a scale airplane that you want to keep scale, a semi-symmetrical wing will give you the greatest flight envelope and slow speed characteristics. A flat bottom wing gives you the absolute slowest characteristics. So fuselage, 75% of the wingspan is the normal rule of thumb. There's some commercial planes like ATRs and other airplanes where the fuselage is basically the length of the wing. But, well, an ATR is not. But there are some planes where it's almost the same. The nose is 20% of the fuselage. So take the length of your fuselage, take where the front of your wing is, and go up 20%. And that's what you want for your nose. Or you move your wing back so you got 20%. Wing to trailing edge is normally 40% of the entire fuselage length. Okay? Horizontal tail area is 25 to 30% of the wing area. Vertical stab is usually 35% of the horizontal stab square inches. So let's think about that for a minute. That is basically building you a good flying trainer or whatever, okay? If it's a scale airplane, all those dimensions are going to come from the drawings that you get created, or you create, or you bought to design off of. Now, I'm not talking about a kit build or a plan-built airplane. If you're building from somebody's plans, you're going to build off those plans. If you're building a kit, you're going to build a kit. But if you're going to draw your own plans and draw your own design, this is some rule of thumbs, okay? So then we got to consider the wing design considerations. And the wing is probably one of the most complicated parts of the airplane, because if you do it wrong, it's a really big, heavy chunk of stuff. If you build it too light, it's not strong enough, and you land and a landing gear might go through the wing, or you pull a high G maneuver and collapse the spar. And I'm going to talk a little bit about how you understand how strong is strong enough, okay? So wingspan, wing chord, airfoil, type of wing construction. You want it to be built up which is normally, balsa wood and sticks and sheeting. It could be balsa wood, some light plywood and sheeting. That's a built-up wing. A foam wing is where you cut it with a hot wire, and then you laminate on balsa wood skins, and then you cut out your parts and pieces. I'm not going to cover right now talking about doing a fiberglass wing from a mold. Some of the jets out there, they basically build a wing out of foam, they sheet it, paint it, put all the rivets on it, and then they pull a mold from that. And then from that, you can pull skins that make your wings. And I'm not going to cover that because I've never done that, okay? I'm only going to talk about what I've done in this video and what works for me, okay? So type of spar system, this is where you need to kind of ask yourself what kind of wing you want. Because if you're building a styrofoam wing, you are normally going to, and I'll use this stabilizer as an example. If this wing was going to have a tube inside it, like a joiner tube and a spar, you would cut this wing, cut this out of foam, hot wire, then you'd put a slice in it somewhere out here so you could put a plywood rib in. You'd have a plywood rib here that has a hole, and those two holes capture what I call the socket, okay? But that foam wing is only strong if this socket is captured in those two plywood ribs because they're dispersing the weight through the wing. If you just slide styrofoam, if you just cut a hole in styrofoam and slide this in here, it's not going to be very strong. It'll only be as strong. Now, I use carbon fiber sockets. If this is a phenolic tube, it would not be strong enough for the airplane. Okay, so I want to cover that one last time. If you are building a foam wing, you're going to hot wire the foam, and before you sheet it, you're going to cut a slice through it and put in a plywood rib that has a hole for where your socket goes in. So when I cut a wing out, I'll have an airfoil shape and an airfoil shape. I'll hot wire cut it out. I will cut the wing about 25% out, 30%. And then what I do is, with the airfoil that I had here and there, I have a hole cut in that airfoil already. So I then slide the airfoil on here, the template, and the template moves out here, put it here, and then I'll go down through the top and I will cut with hot wire the hole that comes out that the tube slides into. But this wooden rib here and this wooden rib is epoxied to that socket. And then the ribs are epoxied into the foam, and once you sheet all of that, those two ribs are supporting almost all the load that goes into the wing and the sheeting of that wing. So there you get your strength. If it's a built-up wing, and built-up wings are more complicated, you're going to take this socket, and it's going to be placed inside the wood ribs inside your wing and epoxy so that this is held in the ribs. Now, I kind of cheat a little bit on a built-up wing. I'll run this because this is carbon fiber and not phenolic tubing, I will run this out to the very last rib I can get. And this becomes kind of a sub-spar. Even though my wing socket, my wing tube, might only go into here, the rest of this is still pretty freaking strong. And it doesn't weigh hardly anything. So that's how I build wings really, really light. So you've got the two different type of constructions of wing, okay? And when I talk about the construction of the wing, be it foam or be it built up, in your plans, in your drawings, when you're engineering this, you need to kind of understand what works and what doesn't work. I've had a lot of people say, Damon, what is the math you use in designing wing? There's no math I use. Well, I don't want to say that. There's not any structural engineering math that I use. What I do is I'll build a mock-up of a spar, I'll take it to my garage, and I'll put loads on it and weights and see what the spar can handle. So here's one thing to think about that I do, and this has worked really good for me so far. So imagine this is in one wing, imagine this is in the other wing, and then between those two, well actually, let me grab another socket here. Sorry people, I am never totally organized when I do my videos, and I should be, but sometimes I just start remembering things once I've started. So, hypothetically speaking here, This is one wing tube in my right wing. This is the other wing tube on my, so left wing, right wing. These are going through all the ribs in my wing. This is a freaking strong spar right now, okay? So let's think about how would I test that? This is a rule of thumb I've come up with, and it's worked in all my testing so far. So take the weight of your fuselage, and let's just use the weight 20 pounds. It's a pretty big airplane. Let's just say the whole fuselage weighs 20 pounds. So what I do is I will normally go out between 55 and 60% of the wing. Yeah, that's right. 55 to 60. I need to check that number. It'll be up here if I'm wrong. But I go out 55, 60% of the wing, and then I'll take the weight I want to test in G. So if it's a 20-pound fuselage, and I would want to put 10 G forces, that fuselage would weigh 10 times. It would weigh 200 pounds. But you got to divide that because you got two wings. So you come out that 55 or 60%, and you put 100 pounds here, put 100 pounds there, support your fuselage, so the same forces in the air are going to be on the fuselage, so you put a stand on the fuselage. You don't want that fuselage to crush, because you might be supporting it in a weak spot. But if you do this right, by going out that 50 to 60% of the wing, it's the same as putting kind of the sandbags all over the wing you see full-scale airplanes do. Keep in mind, full-scale airplanes, when they put those sandbags in, are also testing the skin, the strength of the skin, to make sure it can't collapse. All we're worried about on an RC plane is a spar, because I doubt any of you are going to build so light that your skin can collapse from aerodynamic forces. So the way I do it, and this has worked pretty good, is if I want to test it for 10 Gs, I'll take the weight of the fuselage, divide it in half, and then put that weight on each wing. I think it's 55% of the way out of the span of the wing. And if the wing doesn't break, you're usually pretty good. Now, I don't know if I'm under or over much. I did have an airplane one time where the wings really started to bend at like 12 Gs. I took the airplane out, had a little G meter in it, and I did everything I could to try to get 12 Gs out of that airplane, and it would stall, it would high-speed stall before I could really get 12 Gs. But you could see the wing in a video start to flex when I was at 9.5 Gs. So my guess is around 12 or 13, that wing really started to bend. Now keep in mind, I never destructive tested that wing all the way to breaking. I hate doing that. I will sometimes build a wing just to do that, but if I'm building the actual wing, I hate to do that. I hate to build a whole wing that could be a flying wing and then break it. I've done it before, but I tell you, I'm getting enough experience in my design that I don't have to do that much anymore. So I hope that helps. I'm sure somebody out there on YouTube is going to go, oh, Damon, your calculations are all wrong. Fine, it's worked for me so far. I'm not going to do all the math to understand exactly what the ratio of the weight is over the span of the wing. Okay, I'm just not going to do it. Material used in the spar. Many built-up spars I use spruce as the top and bottom spar. I use balsa wood as a shear webbing, and I'll use either light plywood or balsa as the ribs. Once you put that shear webbing on, and if you epoxy it right, and you really know how to put shear webbing on, you end up with a truss design like you see in a bridge. And that is one of the strongest and lightest spars you can build. The next is doing carbon fiber. I did experiment, and I want to kind of get a little bit into this here. When I designed my big B-36, I made a mistake on the second wing. The first wing was not my fault. The landing gear manufacturer completely lied to me and was a complete douchebag on what they told me their gear would be to fit in my plane. And when I finally bought the gear, it wouldn't fit in the wing, and I had to build a whole new wing for the B-36. So that's not on me. That's on them. But the second wing is my fault. So what I wanted to do is build a spar out of balsa wood, top spar, and I wanted to put carbon fiber on it because carbon fiber in tension does not stretch. Well, it might, but I couldn't get it to stretch in any of my testing. And I use carbon fiber toe, pre-impregnated with fiberglass carbon fiber toe. So I've got a top spar, I got a bottom spar, I got shear web between them. I never thought about compressibility. So when balsa wood is soft, when it compresses, that carbon fiber is not in tension. So it would actually want to lift up off the balsa wood a little bit. So that 21.5 foot wingspan airplane, the wings sagged quite a bit. And I'm like, how can that happen with the carbon fiber? I never thought about compression. So stupid me should have built spruce spars in there, added the 8 ounces of weight, and just called it a day on a 112-pound airplane. So I was just not, it was a bad design. I mean, it's my fault. Now, the B-36 ended up being sold because a guy who's going to open a bar in 2020 wanted to hang it off his ceiling of his bar. And he made me a price I couldn't refuse. So that's where the B-36 went. Now, I did have some pretty evil emails come to me saying, why in the world would you not fly the airplane when it was 95% done? And I'll tell you why. It's a 21-foot, 112-pound model airplane that if the wing collapsed or I lost control of it, it could hurt somebody. You know, I read a guy one time that stood on a soapbox and goes, I can't believe these giant scale guys that spend 10 years building an airplane and then never fly it. That's insanity. Maybe, but to be honest with you, I'm never going to take an airplane into the air that I don't know 100% that it is sound. Now, do I make a mistake and miss something and something could go wrong? Yes. But knowingly fly an airplane that I don't believe in the design will never happen. So, on the wing design considerations, removal of the wings. How do you want them to come on and off the airplane? You really need to think about that. Another thing is the pins that you use on the ribs, not the spar, but the pins that keep it from moving, those need to be about 1 inch long and they should be aluminum shafts. I've seen 2 or 3 videos now where the wing vibrated out just because the screw backed out, and once that pin came out, the whole wing tilt or the horizontal stab tilted and the plane crashed. Those pins need to be 1 inch long, people. They really do. Don't just make little 1/4 inch stubs. They need to go into the fuselage. Engine nacelle placement. Most people think you can just slap a nacelle on a plane and put some fiberglass cloth around it. It's good to go. On a 40 size airplane, that might be right. When you get into 150-inch wingspan planes and you've got 8 horsepower out there, you need to have basically ribs that turn into the mounts for the nacelles on that wing. Type of control surfaces. Flaps and aileron. Now, one thing I'm going to touch on here is a Excel spreadsheet program I created, and I used the math from the AMA 520A document to do this. But as you can see up here, over here on the screen you're looking at, is my ducted fan, and it shows the span of the elevator, the root cord of the elevator, the tip cord of the elevator. My servo from the pivot to the end is 1 inch. The control arm from the hinge point to the end is 1 inch. The airspeed factor from the AMA guidelines, which is 6, which means it's a 140 mile an hour plane or 130, tells me I need 36 ounces of torque. Okay, if you look down at my ailerons, okay, if you look at all that math right there, because my servo control arm is 0.75 and all this stuff, I end up with a 58 ounce torque because of the way it's designed. So keep in mind, there's a lot of math that goes into that. I created a program. If you email me, I'll send you this Excel spreadsheet so you can figure out the size of your flying surfaces. I mean the control surfaces. The MSL-2, my big yellow and blue plane. The elevator was 31 inches across, had an averaged out, and I had to average this out, the tip and root cord of the root cord and the tip cord of 7.4 and 3.8 inches. My servo arm was 2 inch. My control arm was 2 1/4 or 2.4 inches. My airspeed factor is only 1.5 on that airplane because it's just a slow turnaround. But look at how many ounces of torque I need. 405. Luckily, I have a 500, I think it's 565 ounce servo on that. You look at my aileron down there, I need 422 ounces. That's a boatload. Now let's look at the Frau Emmerstein. That's what this is. This is actually an elevator. 1 or 2 elevators on my airplane. This elevator right here needs 955 ounces to work properly. That will be 2 of my, and they're not 500, they're 475 ounce torque servos is what I'm using. That's right, 475. So I'll need 2 of those to operate the elevator. If you look at the aileron, which is this little guy, but it still has a long cord to it, this is going to need 321 ounces. And I've got a couple of 425 ounce servos, so 1 of those will be on this. But when you're thinking control surfaces, you've got to think about your the torque needed to move them. Flaps is the same way. You can put flaps into this little calculator up here, and it'll tell you what your flap torque needs to be. So now we're going to talk about the horizontal stabilizer. Horizontal stabilizer is 25 to 30% of the square inches of the wing. You need to know what airfoil. Unless you've got the whole airfoil moving for trim on certain designs, you will never need anything but a fully symmetrical airfoil. All horizontal stabilizers should be a fully symmetrical airfoil. There's a little bit of reasoning that if your whole stab moves like on a jumbo jet, you might want a semi-symmetrical, and I'll get into that later on. And I know people will dispute it, but some German guy wrote a white paper on it. I thought it was pretty kick-ass. Type of construction, is going to be built up or is it going to be foam? Type of spar used. Basically, you got to think about how you built the spar for the wing. That's what you want in a horizontal stabilizer. Removal of the H-stab. Does it need to come off? If your trailer is only 86-inch opening like mine, and you build a 96-inch horizontal stabilizer, it's not going to go in and out of your trailer. So you're going to need to say, do I need that to come off? Now, one thing I didn't really touch here is flying wires. Okay, if you're building a vintage airplane, those flying wires become your spars. My MSL-1 had no spars run through the fuselage and no spar ran through the vertical stabilizer into the fuselage. Only the flying wires held that airplane together. So you do need to think about that, but I'm not going to cover that in this just because I used real hardware from aircraft sprues, real aircraft cable from aircraft sprues. I used all real hardware on that airplane. So that was the strongest part and most expensive part of that airplane was the hardware for the flying wire. So on the oh, I did skip some stuff. I'm sorry. I skipped some stuff on the wing design. I got to go back to it. Servo placement in the wing. You got to know what you're doing with the servo placement in the wing for the flaps and the ailerons, slats, or anything you're doing. You need to understand your gear attachment points, which are the blocks in the wing for the landing gear. Then you've got to understand the gear wells if there's retracts. How do those gear wells work in the wing? There's a couple of designs out there, and I'm not going to throw anybody under the bus that design B-29s. And these are people that you can buy their plans where they cut the spar in half and expect you to build a little box that wraps around the landing gear. Dumb design. If they would have moved that spar 2.5 inches forward and had another secondary spar about 4 inches behind it, it would have been like a real B-29, and you wouldn't have had to cut the main spar to get the wheel to go up and down. So back to the horizontal stabilizer design. Type of spar, materials used in spars, removal of the H-stabs, servo placements, and then you need to talk about how big my elevators need to be on that horizontal stab. Normally the elevators are 15 to 30% of the square inches of that stab. Some aerobatic airplanes, it is basically split in half. You have 50% of that, that area makes up 50% of your horizontal stabilizer. Vertical stab design. Vertical stab is 30% of the horizontal tail area. Select an airfoil. It's going to be fully symmetrical, okay? It might be a thick one depending on how tall it's got to be for strength. That's another thing you need to think about. On your horizontal stab and your vertical stab, the thicker the airfoil, the more drag, but the stronger it is, okay? Type of construction, built up or foam. Materials used in the spar. Servo placement on the rudder. A lot of pull systems are awesome. Some people will bury it in the tail. I'm not going to tell you how to do that. Just make sure you do the torque calculation. Rudder needs to be 25 to 40% of the vertical stab. The rudder needs to be 25 to 40% of that vertical stab. It needs to be bigger on twins. I'm also going to re-emphasize something I've talked about 100 times. There's been a couple of big twins that's crashed in the last 10 years. Each of them looked like they had 15 degrees of movement in the rudder. There's no point in having a rudder on a twin if you're not going to get 35 or 40 degrees of movement and expect to have enough rudder to steer the airplane if you lose an engine. Look at how much deflection you see on a real multi-engine airplane, how much that rudder moves. Do not build a multi-engine B-25, B-24, B-17, B-29. Do not build a multi and only have 15 degrees of rudder. You want 35 degrees, maybe 38 degrees. I don't know if any went to 40, but you want a lot of rudder movement or it's pointless on a twin. that burns me when I see planes crash. You see them going over and there's just a little bit of rudder going the other way, and I'm like, what the hell? They didn't have enough rudder. Fuselage design, type of design. It could be styrofoam that's glassed and painted, and you pull a plug and then pull a mold and blah, blah, blah. It could be fiberglass. It could be built up balsa. It could be hot wired or sanded down foam that's sheeted. Just design how you want to do that. You got to know your length. Construction, built up, made from a mold, blah, blah, blah. I already touched on that. Wing attachment points are very important. How are you attaching the wing to the fuselage? If it's like an extra where the spar is going to pass through the fuselage, you need to have some really big hard points in that wing with that tube, that socket tube in it, that's going to support. Plus, you need to think the moment arm of that fuselage. Don't build the fuselage so light that the fuselage wants to break in half at the spar. So you need to think about that wing attachment point. It's very important. Vertical stab and horizontal stab attachment points in the back. Extremely important when you're designing the fuselage. Gear design. Do you want a tail dragger or a tricycle? Both are awesome. Both have inherent problems. Okay, you just need to understand how am I going to design that fuselage to accept landing gear. If it's in the wing, all you got to do is worry about the tail wheel most of the time. Well, no, I guess a B-24 Liberator would have a nose wheel with the wing, with the gear in the wing. Same thing with the B-29. Now that I think about it, all big bombers have the wheels and the wings. The only fuselage type airplanes are probably naval and like the A-7 where the gear goes in the fuselage. So I'm digressing. So now we talk about, here's something to think about when we get into landing gear. So that's the next one you're going to see up here. Type of tricycle, retractable or fixed. Type of tail dragger, retractable or fixed. Construction, which is the materials it's built out of. I've designed, I think, 11 landing gears now. And they all worked really damn good. Took a lot of time figuring them out. Some of them were easy, some of them were really hard. But don't be afraid of using steel where steel is needed. Don't be afraid of using aluminum where aluminum needed. Most of the time, the heaviest component on an airplane is the motor and the landing gear. Literally on the B-36, my landing gear weighed 21 pounds. That's one of the reasons I went to carbon fiber shafts and some other things, because it was just stupidly overbuilt. Stainless steel in places it didn't belong. It was a mess. And I'll never buy commercially made landing gear again. I'll make them myself because I know they'll work and I can control weight. The way they attach the wing is really important. Don't build a landing gear that's got 4 little screws holding it into the wood that are like wood screws. It may pull right out of there. You need to figure out how to make that landing gear lock into the wing or the fuselage so that you know that it's going to destroy the fuselage. Now, I know people get mad at me when I say that. They're like, well, shouldn't the gear come off and you protect the fuselage? If it's a trainer, or if it's an extra, or it's a laser, if it's an aerobatic airplane, sure, it's better to have the gear come off than destroy the fuselage. But I would rather have my gear strong enough that, well, keep in mind, if you're landing hard enough to destroy the landing gear and the way it's mounted to the wing, you're a horrible pilot. Sure, we all make mistakes, but come on. If you're going to really land hard enough to have a nice retract system, not fail but destroy the airplane, you've got other problems. And I know I'm going to get some hate mail on that. I don't care. You got your wing attachment, fuselage attachment, then you got your gear doors. I don't know how many times I see people design landing gear and the gear don't go up all the way, or they go up and the doors don't close. And I keep thinking, you made a great pizza, but you forgot the pepperoni. Okay? Make sure that you design every component to work. Don't build the greatest gear in the world and then say, oh, the gear door is an afterthought. I'm going to put a spring with a rubber band on that. When the gear closes, they'll pull it shut. Design it. Design it. Design it. Then brakes. What kind of brakes are you going to put on? As you know, all my airplanes have brakes. And I love brakes. I mean, it's so cool to land and stop quick, or to lock up one wheel and taxi and pivot on that one wheel. I love that. So now we're going to talk about the power plant. And this is where I'm going to try not to be biased. You got glow engines out there, and if you got a glow engine, you got a fuel tank that goes with it. You got to have a way to fuel that glow tank. You've got to have the buddy box with all the stuff that goes with making that glow. You've got to seal the firewall chemically so that fuel can't get in there and eat up all your glue and plywood. So glow is awesome, but it has its challenges. The thing I love the most about glow is you can put a 16-ounce tank in some small 40-size planes and fly like for 35 minutes. Electric, you can't do that. Then you got gas engines, which up until 10 years ago was my favorite thing. The 3W150 twin gas engine on my half-scale pits was one of the greatest gas engines I ever owned. And I loved that engine. And it was an absolute blast to own and fly. You got to think about the fuel tank system, the fuel filter systems, and all that. If you're building a twin, listen to me. If you're building a twin and designing a twin, if there is any way to build around electric, you should do it. But if you're not into electrics at all, then don't do it, because the learning curve on electrics is about 18 months. But if you're going to put gas engine in a multi-engine airplane, make sure you have strain fuel, filtered fuel. Make sure that that engine has run in another airplane at least 10 hours. Make sure it will idle for 24 hours without dying. Make sure that motor will never die. And then when it still dies, make sure you got enough rudder to fly the airplane, okay? You got ignition system. You got kill switches. If you're electric, you got the motor, the ESC, and battery placement. This all needs to be figured out where it's going to fit in your fuselage. Then you've got to start thinking about maintenance. Okay, how do I maintain that airplane? How do I understand that airplane? How do I make sure things aren't shaking apart? Okay. Then lastly, we talk about the radio. Type of receivers you're going to use. Do you have telemetry or not? Then you say, how many receivers do I need? Here's a rule of thumb. This big transport's going to have over 36 servos in it. I made up my mind several years ago, the moment I get over 18 servos, the moment I have more than 18 servos, I'll use another receiver, because I want to share that load. When you start thinking of 18 servos, some of them possibly pulling 3 amps, you start thinking about 22 gauge wire, you can really start to pull your battery down the system fast. So what I do is I go 2 receivers, 2 batteries each. I use 22 gauge wire, and sometimes if I have a servo at the ass end of the airplane, I will run a wire per home run per motor so that I make sure that I'm not overloading one of those wires. Okay? Make sure you've got plenty of headroom on your battery for it to pull amperage. Make sure that you just really go through that system, make sure everything really, really works. So then you got to think about the placement of your receivers. Then you got to think about the type of batteries that are going to power your receivers. Then you got to think, do I want a power box or not? Power boxes are great. And I might be told I'm wrong, but I don't think there's power boxes that are working really great with S-Bus yet. I could be totally wrong there. I haven't researched it, so don't yell at me. Then you got to think about your wiring harness. Am I going to make it? I bought one of those Hanson Hobbies so I can make all my own servo connectors and all my own harnesses. You know how to solder. I'm not kidding. And then lastly, the switches for that big airplane. Where are all your switches for the receivers, for the electric landing gear systems, and all of that? So in a nutshell, that's what I wanted to cover. Now, the last thing I want to talk about, if you're over 55 and under the 77 pounds, 2 ounces, you can inspect the airplane yourself. Since you built it, you know exactly what's in that airplane. If you're going to be at 77 pounds, 3 ounces, up to 125, an inspector is going to look at that airplane. So when you're building the airplane, you want a massive amount of documentation. You may want some service hatches, inspection hatches on the airplane that you can pop off and let the inspector look in there. So just keep in mind that you need to make the airplane so that you can get it AMA legal. So I tried to compress a massive amount of material into this video and help share with you kind of what I look at as my basics, my rule of thumbs for designing my airplane. I'm not going to get into the design of the airplane. I'm talking about how once I've selected and I've done my drawings, this is all the things you need to think about. I'll do another video on the design. When I first start my first sketch, when I first go into AutoCAD, when I first take it into 3D and what I do to 3Ds, what parts might get 3D printed, and how do they have to be 3D printed to be structurally sound. There's like this hinge here. You know, I was on a forum and posted that this hinge I designed, okay, and this is a 3D printed hinge, and this will actually, so this part right here is embedded in the wing, fiberglassed in, it can't come out. This piece here is embedded in the wing, and then this is held in with 440 button head screws. So somebody had to be a jackass on the forum and say there is no way a 3D printed like that will work. Well, keep in mind, I know which way to run the grain. I know how to design in 3D. So when I took this hinge right here and mounted it to a table, I was able to put 165 pounds on this before the hinge started to pull apart. It didn't break. It was pulling, it was starting to turn the 440 screw sideways out of the ABS. So if I can get, and I need to look at the numbers, I might have been 178 pounds and 4 ounces or something like that. But it was insane. This hinge will pull out of the foam and fiberglass and everything way before this hinge will fail. Okay? So that's all I want to do in this video, everybody. I hope you find these informative. I hope they're not too redundant. And look, I'm not getting high-tech in my videos, okay? I see people that are out there monetizing their videos. They're going to Patreon and trying to make money. I've got a real job. I've got an awesome family. This is my hobby. I don't have a lot of time to edit videos. I don't have a lot of time to really do high-tech stuff in my videos. So understand this, that I'm just trying to be a teacher, and I'm trying to share my knowledge with you, and we're just getting together in my shop and hopefully learning something together. So keep the emails coming. Keep the private messages coming. On Facebook, it's Damon Dag Attwood. So just type in DAMON DAG ATWOOD, and you'll find me on Facebook. And that's where I post all my designs and all my stuff. I don't go to forums much because, at least on Facebook, most of the time you can't create that you're Richard Nixon. Okay, you're a real person, and most people that are a real person, they don't become jackasses in an open forum. Going to RC groups, Flying Giants, and all those places, the trolls were just too much for me. So thanks, everybody. You have an awesome day, or awesome night, because it's late. It's real late. It's 11:12 at night here. And thanks for watching, everybody. Have a great night.